Hello, welcome to the NPTEL online certification course on deep learning. In our previous lecture, we started discussions on the topic in neural network, and we have talked about implementation of two of the logic functions, the AND logic and OR logic using the neural network. And we have seen that AND logic and OR logic, both of them being linear functions, they can be implemented very easily using a single neuron. These single neurons are known as, or a single layer neuron, they are known as single layer perceptron. We will see later that why they are single layer perceptron. Today, we will talk about other implementations of neural network like XOR logic. We will also talk about feed forward neural network or a multi-layer perceptron, and we will also talk about how the neural networks can be trained using a learning mechanism known as back propagation learning. So, let me just recapitulate what we did in our previous class. We have implemented two logic functions, AND logic and OR logic, and we said that both this AND logic and OR logic can be implemented using single neuron or single layered neural network. So, for implementation of an AND logic, what we have done is we have taken our input vector to be 1, x 1 and x 2, and the weight vectors were taken as minus 1.5, 1 and 1. In the neuron, I can consider that it has two functional parts. In the first part, it computes W transpose X. So, in this case, it will compute W 0, which is nothing but minus 1.5 minus 1.5 times 1 plus 1 into x 1 plus 1 into x 2. So, effectively this function which is computed is x 1 plus x 2 minus 1.5. Now, this computed value is passed on to the second compartment of the neuron, which computes the nonlinearity, and in this case the nonlinearity is a threshold nonlinearity. So, the nonlinear function that we have considered is a threshold nonlinearity. So, for x transpose W transpose x greater than 0, the output is 1. For W transpose x less than or equal to 0, it is equal to 0. So, as a result, at the output, the function that I get is an AND function. So, this is what we get in case of an AND function when the input vectors are minus 1.5, 1 and 1. When I want to compute an OR function, I simply, my input vectors remains the same, that still is 1, x 1 and x 2, whereas weight vectors are changed to minus 0.5, 1 and 1. As before, the first compartment computes W transpose x, and the second compartment gives you the nonlinearity, which imposes threshold nonlinearity in W transpose x. So, as a result, at the output, what we get an OR function, OR of x 1 and x 2, and here with this weight vector, the classifier that we are doing, or the separating plane that we are designing, is nothing but x 1 plus x 2 minus 0.5, that is equal to 0. That is the separating plane between the two classes omega 1 and omega 2. And we have also said that we could implement AND function and OR function using a simple single layer neuron or a single neuron, because the classes in this case are linearly separable. Now, what happens if the classes are not linearly separable? So, we have discussed earlier that in non-linearly separable cases or linearly non-separable cases, Either I can have a nonlinear classifier, that is the boundary which itself is nonlinear, or the other approach can be that you can map the feature vectors using nonlinear functions to an intermediate feature domain, where because of this nonlinear mapping, in the intermediate feature domain, the feature vectors will be linearly separable. And as in the intermediate feature domain, the feature vectors are linearly separable. So, I can now have linear classifiers which classifies the features in the intermediate feature domain. So, I have two levels of operation. In the first level of operation, the feature vectors will be non-linearly mapped to an intermediate feature domain, where they will be linearly separable. And in the second step, these feature vectors in the intermediate feature space, where they are linearly separable, in the second step I can design a linear separator or a linear classifier which classifies these vectors in the feature space. Okay. So, I have a nonlinear mapping of the feature vectors in the original space, and finally, a linear classifier. So, let us again see a very simple example. What happens that in case of instead of AND function or OR function, if I want to implement an XOR function. So, all of you know that in case of XOR function, when the inputs are 0 0, that is both x 1 and x 2, both of them are zeros, the output is 0. If both of them are 1s, that is x 1 is equal to 1 and x 2 is equal to 1, then also the output is 0. Only when the x 1 and x 2 are different, that is in case of 0 1 or 1 0, the output will be 1. So, that is what I have in case of XOR function. And in the same manner as we have done before, if I want to plot this in the feature space, if I plot this feature space and plot all these feature vectors in x 1, x 2, that is 0 0 0 1 1 0 and 1 1 in this feature space, then this is the situation that I have. You find that when x 1, x 2, both of them 0, then the output is 0. If both of them are 1, then the output is 0. If they are 0 1 or 1 0, then the output is 1. And now find that I have a difficult situation. In the earlier cases, when we talked about OR function or AND function, the classes were linearly separable. On one side of the straight line of a straight line, I had the value 0, on the other side the values were 1s. But here you find that the values of zeros and 1s cannot be separated by a single straight line, rather I need two different straight lines. And in between the straight lines, the values are 1, and outside the straight lines, the values are zeros. So, this is a clear case where the problem is not a linear problem, but it is a nonlinear problem. So, can I implement this XOR function using neural networks or neurons? Let us see. So, you know from your digital circuits course that an XOR function x1 or x2, x1 XOR x2 can be broken into a multiple stepped function. So, what I can do is I can perform OR operation of x1 and x2, and I can also perform NAND operation of x1 and x2. So, here what I have, this first I compute x1 or x2, and the second one is NAND operation of x1 and x2. Obviously, this is not NAND operation because this is nothing but x1 and x2 complement of that, which is nothing but x1 complement or x2 complement. So, I perform AND operation of x1 x2, I perform OR operation of x1 x2, I perform NAND operation of x1 x2, and these two outputs, the AND output, OR output and AND output, I AND them together, and that gives me x1 XOR x2. So, effectively what I am doing is, as shown in this particular table, I am converting the input vectors x1, x2 to an intermediate vector h given by components h1, h2. So, here you find that if I consider that output of the OR operation is h1 and output of NAND operation is h2, as we have shown here, then when the input is 0, 0, h1 will be 0 and h2 will be 1. When the input is 0, 1, h1 will be 1, h2 will also be 1. When the input is 1, 0, h1 will be 1, h2 will also be 1. And when the input is 1, 1, then h1 will be 1 and h2 will be 0. So, as we have done before, if I plot h1 and h2, that is the intermediate feature space. So, say this is h1 and this is h2, you find that when h1 and h2, they are having values 0 and 1, h1 is equal to 0, h2 is equal to 1, which is the mapped x as x1 equal to 0 and x2 is equal to 0. So, I have h1 0 and h2 1. This is where I want my XOR output to be equal to 0. Similarly, when the values are 1 1, both h1 and h2, they are 1 1, which is equivalent to x1 is 0 and x2 1, or x1 is 1, x2 is 0. In both these cases, I want the XOR output to be 1. Sorry, I just made some mistake. So, over here, when the h1, h2, both of them are 0, x1, x2, both of them are 0, that is h1 is 0 and h2 is 1. So, this was correct, right? So, here I want the output to be 0. In the other case, when x1 is 0, x2 is 1, or x1 is 1, x2 is 0, which are mapped to both h1 and h2 becoming 1 1, I want the output to be 1. So, here I want the output to be 1, which is the case when both x1 and x2 are either 0 1 or 1 0. And in the other case, when x1, x2 are 1 1, I get h1 to be 1 and h2 to be 0, that is somewhere over here, and here my XOR output should also be 0. So, you find that now I have, this is the place where I have XOR output 0, this is the place where I also have XOR output to be 0, and this is the place where I want to have XOR output to be 1. And now you find that they are linearly separable. So, the first nonlinear mapping, or the first step, in the first step, when I am computing x1 or x2 and x1 NAND x2, these two operations are transforming my input vector to an intermediate vector given by h1 h2. And in this intermediate space, in this intermediate feature space, the problem is linearly separable. So, now I can have a linear classifier to classify the input vectors x1 and x2, where the linear classifier, instead of operating on x1, x2, the linear classifier operates on h1 and h2. So, I can represent this again in matrix form. So, what I have is, in the first level I have a set of matrices given by set of weights given by the matrix W1. So, these weights are, so if you look at the first one, it is minus 0.5, 1, 1, which are the weight vectors we have used for an OR operation. The second one, the second weight vector is given by 1.5, minus 1, minus 1. And if you remember from our previous discussion that minus 1.5, 1, 1 was the weight vector corresponding to AND operation. So, if I negate it, I make it plus 1.5 and this as -1 and this as -1. This is the weight vector which is used for NAND operation. So, using these weight vectors, I compute W1 transpose X, where W1 is actually the weight matrix consisting of -0.511 and 1.5 -1 -1. So, this is my intermediate, the matrix product that I get. Now, if I apply the nonlinearity, which is a threshold nonlinearity, I get 1 0 0 0 1 1 1 and 1 1 1 0. That is my intermediate set of vectors which is given by matrix H. So, this is my H1, this first row corresponds to vector H1, the second row corresponds to vectors H2. So, my final output, if I put another weight vector, now you find that this weight vector corresponds to an AND operation, that is -1.5, 1 and 1. This was my intermediate matrix or set of intermediate feature vectors H1 and H2, which is given by H. So, if I compute H transpose W2 now, the output of this matrix multiplication becomes -0.5, then 0.5, 0.5 and -0.5. Again, I pass this through this threshold nonlinearity and I get the output as 0, 1, 1, 0. So, you find that when my H1, H2 are 0, 1 or 1, 0, the output becomes 0, and these are equivalent to the input vectors being 0, 0 or 1, 1. And when my H vector, that is the intermediate features, are 1, 1, that is this case, the output is also 1. And this is the case when both x1 and x2, they are either 0, 1 or 1, 0. So, I have implemented this XOR function in 2 steps. So, I can consider this to be implemented using 2 layer neural networks. In the first layer, I will have 2 neurons, one giving an OR operation and other one giving an NAND operation. And you find that because AND is a linear problem, NAND is also a linear problem, because NAND is nothing but complement of AND, and that is what we have done over here. That plus 0.1 plus 1.5 minus 1 minus 1, this weight vector actually gives a NAND operation. Okay. So, I can implement this XOR operation, which is linearly non-separable, but for implementation of this, as obvious from this operation, that a single layer neural network or a single neuron is not sufficient. Rather, I need 3 neurons, and those 3 neurons are to be arranged in 2 layers. One neuron in the first layer will compute OR operation, the other neuron in the first layer will compute NAND operation, and then the third neuron, which is in the second layer, will combine the outputs of these neurons in the first layer using an AND operation to give you the final output. So, effectively, the kind of neural network that I have is this. So, here I put my input to be again 1, x1, x2. Suppose this first neuron computes OR operation. So, we know that for OR operation, my weight vectors should be minus 0.5, 1 and 1. And suppose this second neuron computes NAND operation, for which I have to have weight vector as plus 1.5, minus 1 and minus 1. So, here what I get is x1 or x2, and here what I get is x1 NAND x2. So, I use this as H1 and this as H2. And the third neuron in the second layer, this computes AND operation, So, here I have to have the weight vectors as minus 1.5, 1, 1. So, this performs an AND operation, and finally, at the output what I get is XOR of x1, x2. So, I get x1 or x2 at the output. So, through this discussion it is quite clear that if I have linearly separable problems, single neuron for a 2-class problem is sufficient. If I have multiple classes, then I have to have multiple neurons. So, in case of multiple classes, the way this has to be done is I can have a number of neurons, but in a single layer. Here I have the weight vectors, say something like this. So, here I have x, over here we have the weight vectors, a set of weight vector for this neuron, a set of weight vectors for this neuron, a set of weight vectors in this neuron. Each of these neurons performs, suppose the weight vector for this is a W1, weight vector for this neuron connecting to this neuron is a W2, weight vector connecting to this neuron is a Wn. If I have got n number of classes or n number of categories, this neuron will compute W1 transpose x, and then a function of this one will compute W2 transpose x, and then a function of this one will compute W n transpose x and a nonlinearity on this. So, I will get a number of outputs O1, O2 and O3, which actually gives you the score functions or score values for different classes or different categories corresponding to input vector x. And here you find that all these are linear combinations of different components of the input vector. So, if my problem is a linear problem, I can solve it using single layer neuron or single layer neural network. But if it is not a linear problem, if it is a nonlinear problem, that as has been demonstrated with a very simple nonlinear function of XOR function, I need multiple levels of neurons or multi-layer neural network. So, the kind of neural network that I have to have over here is as given by this. You find that every layer of the neural network computes a nonlinear function of the input feature vector, of the feature vector inputted to that particular layer of neurons, and the output of that layer of neurons is an intermediate feature vector, maybe of same dimension or maybe of different dimension, depending upon how many neurons I have in that particular layer. We will see that as we proceed through our discussions. But effectively what I have is, I have a multi-layer neural network, and in every layer the neurons compute a nonlinear function. So, when I have a cascade of these nonlinear functions as given by the multiple layer neural network, as has been shown in this particular diagram. So, here you find that suppose each of these are neurons, a layer of neurons, and in every layer it computes a nonlinear function. Say in ith layer it computes a nonlinear function f I on the feature vectors which are computed by the previous layer given by the function f I minus 1, and each of these are nonlinear function. So, I can cascade all of them together to give you an overall cascaded function as given by this. So, if my input vector is x, the first layer computes f1 of x. This f1 of x is inputted to the next layer. So, which computes f2 on this f1 of x. That means, this layer computes f2 of f1 of x. And this way it continues. When it comes over here, say I have a set of mapped feature vectors over here, which is given by say h k minus 1, which is a mapped feature vector mapped from this vector x through a series of nonlinear mapping, where each of these layers of neurons gives some sort of nonlinear mapping. And then I have a final layer of neuron, which is the kth layer, which when I come to this hk minus 1, these feature vectors are nonlinearly mapped from x, and as these are nonlinearly mapped, so this in this feature space as given by this vector hk minus 1, these feature vectors are the problem that is posed is a linearly separable problem. And once I have such a linear problem, the final layer or the kth layer can solve this using a linear discriminator. So effectively, I can put all of them in a cascade of operations, something like this. Okay. So at the first layer, you compute f1 of x, which gives you say set of feature vectors h1. In the second layer, you compute f2 of f1 of x, which gives you a set of feature vectors say h2. So you find that each of them are nonlinear mappings. Over here, through this cascading operations, I get a set of feature vectors say h k minus 1. And when I have this h k minus 1 in this feature space, as these are nonlinear mapping of x, I can have a set of nonlinear mapping such that h k minus 1 will lead to a linear problem or a linearly separable problem. And once I have that, the final one, that is f k, can be a linear machine, or it might be a linear classifier. So I have a set of operations which maps an input vector non-linearly into a space where they are linearly separable. And once they are linearly separable, then in the final step, I can have a linear classifier. That is what a multi-layer feed-forward neural network does. And why is it feed-forward? Because you find that the information is always flowing from input to output, right? The information does not flow in the reverse way. Of course, there are other variants of the neural network known as recurrent neural network, where the information can also be fed back. We will come to that later. And here you find that the number of such cascading stages, here the number of cascading stages, which is equal to k, this tells you what is the depth of the network. So in this particular case, the depth is k. And as the value of k increases, that is the number of layers increases, the depth also increases. And this is this term, that is the depth of the network, which actually is converted to the concept of deep learning or deep neural network. Okay. So the more the depth is, you are moving deeper into the problem. So the deep neural network or deep learning concept actually comes from the depth of the network, or the depth of the network giving you the nonlinear transformation. It is related to that. So I'll stop here today, and I will continue with the discussion in our next class. Thank you.